I've given this a title, High Energy X-ray Microscopy, Insights into Additive Manufacturing. I am inevitably going to touch on several different subjects. In fact, I realize even this long list of co-authors doesn't really cover everything, but I'll try to remember to give credit where it's due. The slightly odd-looking picture in the bottom left has to do with a recent sojourn in Ghent in Belgium, thanks to the Franke Foundation, which was very, very pleasant, I have to say, and a welcome change from the confines of COVID. Okay, so a lot of what you're going to see owes a great deal to working at APS, but I mainly need to acknowledge the manifold efforts of my group as well as my collaborators, and a rather wide range of support, some of which you'll notice is very much focused on actually rather practical 3D printing. Other projects are more nearly basic science issues. And as you might imagine, I'm going to more emphasize the latter and not bend your ear about things like high temperature heat exchangers, interesting as they may be. So there are a number of different topics that I'm going to cover. I will talk very briefly about high-speed imaging, just because it's shown us so many things. I will tend to emphasize high-rate diffraction, but I am going to give you a couple of examples, and I'll actually do it up front about 3D microscopy, because it does make a connection to high pressure and shock experiments, even though the main experiment I'm going to describe goes back about almost 10 years at this point. If I have time, I'll briefly introduce you to what we've been doing with Bragg coherent diffraction imaging, which will again take us away from the printing and more towards techniques. So as Russ indicated, I am a co-director of something we call the Next Manufacturing Center. And this has quite a broad scope, mainly in metals additive manufacturing. We do have a pretty good set of equipment, so we do our own printing. We cover a lot of different aspects of it. So I would say that it provides a very useful basis for sort of jumping into what reveals itself as interesting problems. So let me give a very quick example, which I think will resonate with one or two of you. Some years ago, as part of BES's activities, Basic Energy Sciences, there was a look into what actually is mesoscale science, and does such a thing even exist? So this slide I owe to George Crabtree at Argonne, who came up with this contrasting view of reductionist science, which is perhaps what most of us typically do. We start with a phenomenon and we work our way down to perhaps the ab initio approach to it, as opposed to what one tends to do on the simulation side of things, and we try to build up from the most basic information that we have. And so you can contrast this reductionist versus this constructionist approach. For me, I've been mostly interested in defects and how they affect mechanical behavior. And so the BCDI that I mentioned is pretty interesting for being able to directly image defects actually in the bulk, instead of relying on, for example, thin foils in transmissional electron microscopes. But the high-speed imaging has brought me to looking at phenomena such as keyholes in laser melting. I will show you a couple of examples of taking diffraction patterns at relatively high speed, not as high repetition rate as the keyholes, but nonetheless very revealing. I spent a lot of time looking at grain structures, and I'm showing you an example of a characteristically complex, if not jumbled, microstructure that you get out of printed material. But one of the essential problems in 3D printing is that many of the materials that you would like to use that have good properties in many respects unfortunately will crack when you try to print them. In other words, do high-speed, high-rate solidification with them. And that's yet another phenomenon that's been very amenable to high-speed imaging. I'm going to show you some examples of diffraction microscopy. That little tiny diagram is trying to indicate how you actually execute an experiment. And then, of course, in some part of what we do, we make actual parts that we go off and do engineering tests on. So not much of that today. A colleague, to my considerable amusement, pointed out to me that material science struggles actually with which of these approaches to take. So Ashby's classic textbooks are very much reductionist. Start with the phenomena that engineers need to know and work your way down to whatever length scale is required. Whereas other classic textbooks, such as Callister's book, very much start with the basics and try to build their way up to the engineering phenomena that are of interest. Okay, so much for the 30,000-foot view. But very much happy to debate with you what mesoscale science is, which reminds me to say one example pertains to dislocations, where we know perfectly well what the properties of dislocations are. We can calculate them to a very large extent. But when we try to connect dislocations as individual defects to, for example, work hardening behavior, you deform something, it gets harder. How do we calculate that from first principles? Pretty tough problem, not really a solved problem as yet. So it's an example of mesoscale science, in my head at least. Okay, so let me walk you extremely quickly through what is high energy diffraction microscopy. The basic idea is remarkably straightforward. You mount your sample on a rotation stage in front of a monochromatic high energy beam, for example, at 1 ID at the APS, and you take a diffraction pattern. But more than that, what you want to do is take a diffraction pattern at more than one sample detector distance. So that's that diagram there. And furthermore, you take that sample and you rotate it by a very small increment and you repeat. And you repeat and you repeat until you have this stack of diffractograms that contain overlapping diffraction patterns from all the grains illuminated in a given layer. So that's what the green circle is supposed to indicate. And I hope you will believe me that software exists to take all of that diffraction information and extract from that, basically through forward modeling, what is the grain structure? What's the orientation map in that region, in that illuminated region? And then to get your 3D structure to repeat, there is a variant of it that we call far field, which you don't get very much spatial information, but what you do get is elastic strain information. And that complements very nicely what the far field will do for you. So the typical spatial resolution is 1 to 2 microns. The orientation resolution is very good, 1/10 of a degree or better at times. And it's not just APS, you can do this other places, CHESS, ESRF, so on and so forth. Then to complement that, you need some way to calculate, at least we do in the kinds of problems we look at, to calculate full field micromechanical simulations. In other words, take the measured structure as the input and calculate for a given loading, what is the pattern of elastic strain and elastic stress, plus plastic deformation where appropriate. And most people would use finite element. We use a code that we like to refer to as MASSIF, micromechanical analysis of stress strain inhomogeneities with Fourier transforms. That's a rather fancy title for a code that's basically a spectral method and exploits the Green's function approach, but putting it all into frequency space to speed it up. That's the point of using the FFTs. And it turns out to be a very convenient computational technique that allies with either 2D imaging, such as EBSD, or 3D imaging, of the sort that I described in the context of HCDM. So what is all of this good for? And how does it in some way relate to 3D printing? Well, there have been more and more simulation challenges that have been put out for the community to work with. The better known ones in 3D printing are the so-called AM bench exercises that NIST has put out now 2 rounds of. But the Air Force Lab, AFRL, also put out a simulation challenge that was much more closely related to the kinds of techniques that I just briefly summarized. So what they did was to take a sample of printed Inconel, nickel alloy, 625, measure about a cubic millimeter of it, publish the microstructure, publish the stress strain curve, tell us what the elastic properties would be, and then ask us to predict the state of elastic strain in 28 individual grains inside that measured volume that contains, let's say, 1,000 grains total. And this was challenge number 4 out of the 4 challenges that were offered. We used their HCDM data, and we ran this FFT method, collaborating with Ricardo Levinson at Los Alamos, who's the origin of this, fitting the stress strain curve, and then comparing the elastic strains, full tensor, in each of those 28 grains against the measurements. And this error plot here shows you where we started. So we started with these error values, so decent, getting less good as the plastic strain accumulates, but it was good enough to actually win that challenge, to our pleasant surprise. What was particularly interesting was to come back to the problem after the fact, after the selection had been made, scratch our heads and say, I wonder if we missed something. And sure enough, we did. It turned out there was more information in this initial data set than we had understood at the beginning. And when we included that initial information in the appropriate way, we were able to knock down these errors by a factor of about factor of 2. And so we reckon that we were doing quite a good job in the elastic range, but less good as you get into the plastic range. And so if you're not very impressed at how well we're matching things when metals go plastic, I don't blame you for thinking that, but I can assure you that this is the same story that we've been seeing from many, multiple sources, which is interesting. What else do I need to say about this? This was largely the work of an undergraduate, Carter Koch, at University of Utah, working with Ashley Spear, as well as myself and Ricardo Levinson, and a very capable individual who's now in graduate school at Caltech. So good for him. But the point was, it was an opportunity for validating microscale plasticity for more complex systems. And this was printed material. So this was a challenge based on 3D printing. Okay, so I will continue on to revisiting some history, if you like, or at least an experiment done a few years ago. And when I retrieved this particular set of slides, I was very pleased to see that there was a picture up here in the top right of not the actual piece of apparatus that was used, but something very closely related that was actually done by your center, Russ, in other words, CDAC, and it was a miniaturized spall experiment. And so John Bingert and colleagues at Los Alamos did a very similar experiment in which they mounted the sort of canonical millimeter cubed inside a bigger piece of copper. That's the piece in here, so that they could then embed it in an impactor and target assembly and do a partial spallation experiment. And the miracle in this was that we had the millimeter cubed, we measured it at 1 ID, we sent it back to Los Alamos, they did the experiment, And then poor old John Bingett had to scramble around the chamber and somehow go find this little tiny piece of copper, which he did, and send it back to us in time for the scheduled beam time. But it worked. It all happened. Okay, so what we did with this was to, from the initial experiment, which which allowed us to map the entire microstructure. So that's this colored picture here with a cutaway, and then take the recovered piece. And it turned out that the main point of the recovered piece was to do computed tomography so that we could locate all of the voids. The shock trapping wasn't perfect. The spallation, the incipient spallation, the voiding occurred in a curious sort of donut shape. But nevertheless, there were plenty of voids there, several hundred of them. And thanks to being able to repeat the mapping and register the voids and the second mapping back onto the original experiment, we were able to correlate where those voids occurred in relation to the microstructure. So the motivation for this experiment was, what is the link between the microstructure and voiding under these conditions? Is there a microstructural feature that is predictive of those voids? And I remind you that the more or less classical idea is you just have to look for the places in the material where you have the smallest pressure, the most negative pressure, or the largest tensile traction, if you like, across some surface, or across some cross section. And that's been, a fairly typical thing to use in damage modeling. And in case you're curious, the answer is it didn't work. So let me elaborate and say, let me skip over the iron 100 pause. So David Menache in particular was able to take that void structure, lay it on top of, register it with the original measured microstructure. There were north of 400 voids, of which about 3/4 of them were close enough to grain boundaries to be considered grain boundary voids. So it was in fact grain boundaries that we mainly focused on. Since a grain boundary is a dividing point between two different orientations of the crystalline material, and presumed to be a place that would maximize any, shall we say, untoward behavior. And so what we ended up doing was embedding the actual cylindrical piece inside a square block for convenience in the modeling. There was a lot of detail that had to be entered into with help from people like Kurt Bronkhorst. And then we went looking for correlations. So one of the first stops, as it were, was to say, well, surely it's the hydrostatic stress or the traction across each of those grain boundaries. So we looked for differences in the pressure across grain boundaries versus other locations. And so the red violin plot is for grain boundaries, and the blue is for, I guess, for other locations, sorry, the rest of the microstructure. And we could not find any significant difference. I mean, it really was a null result. There was nothing about the state of hydrostatic stress at the grain boundaries that could explain those voids. And so there were only two things very closely related to each other that seemed to show any separation in these two distributions. One was to look at a quantity that is called the Taylor factor. So the Taylor factor is something very specific to what we call crystal plasticity. In other words, the study of how you relate dislocation slip to external stress strain behavior. And Taylor factor is a scalar number that more or less tells you the ratio between the slip system strength and the macroscopic strength that you can observe. And so in this case, we did find some separation in terms of the difference in Taylor factor across grain boundaries. We measured it with Hellinger distance. It's a bit equivalent to a correlation coefficient. It's suggestive at this level, but it's by no means a slam dunk. And you'll just have to trust me that it's the only indicated that we could find that would do this. Now, you can look at a more detailed quantity, plastic work. That's a bit more akin to integrating the work done during the actual plastic work, which is not a large amount of strain, plastic strain, non-recoverable strain, but it's certainly non-trivial. And that showed a slightly larger separation in the two distributions. But what was interesting was when we talked to other people who, for example, did molecular dynamic simulations, they had, previous to our efforts, found something similar, although they were looking at a very small number of special grain boundaries in their simulations. Whereas I do want to emphasize that this was, in some sense, a statistical result. In other words, looking at an entire collection of voided grain boundaries. And that is basically where we ended up. That was the net result of the effort, and something that I and my colleague Bob Suter would very much like to get back to. The modern tools have improved such a lot. It seems like it would be well worth doing and should have significant impact on damage modeling. All right. So now I'm going to turn to actual printing, and in whatever time remains, I'll stop at 45 minutes, I think, trying to give you some idea of some of these experiments that we've been doing where high-speed visualization and diffraction has been so useful. So perhaps not all of you are intimately familiar with the basic physics of 3D printing of metals. Many people call this micro welding. In other words, the dominant technology is laser powder bed fusion, which just means you spread a layer of powder, come along with your laser, and wherever you want solid material, you melt it. You do this such that the spot size is typically about 100 microns, and the melt pool that you generate, moving at typically a meter per second, is a couple of 100 microns wide. And that means that for a layer thickness of order, say 40 microns, you need kilometers, many kilometers of these melt tracks in order to build your part, which means that it's very slow, can take 2 or 3 days to print your part, so that makes it rather expensive. Nevertheless, the typical cooling rates that you can get to there in the third bullet are on the order of 1 million degrees per second. And that means that the dendritic or columnar microstructure that you get has a characteristic length scale more like a micron, 1 micron, as opposed to the hundreds of microns that are typical in normal solidification. The solidification speed is basically set by the scan speed and also heavily influenced by the melt pool geometry. So it's typically less than a meter per second. We have some technical issues with going faster than that. Lots of interesting things there. The last bullet is mainly making the point that the phase structure of what you get is typically rather different from what you expect to see in conventionally processed material. So that's one of the many motivations to study these phenomena. Well, I always like to put things in historical context. And so the context here is the cover page of some proceedings from the 1980s. Robert Moravian might be a name that's known to you. That's actually, it's literally 1980. It was the third conference on rapid solidification processing. It was, at the time, an exciting possibility of a technology. Problem, all it would produce would be basically little splats or ribbons of very thin material. And it was not at all obvious how you could in any practical way build up real parts. So the difference is now with this technology, you can build real parts and, at least in principle, make them as large as you like, but all with rapidly solidified material. All right, so let's turn our attention to the actual melting process. Again, I'm sorry if you've seen these videos many times before, but maybe not everybody has. What you're looking at is a movie where we've done this at 32 ID, and we are sending pink beam actually through a sample. It's a couple of millimeters wide. And what you're looking at is not the melt pool. You're seeing the vapor hole. The intensity of the laser light is sufficient to not just melt the metal, but actually boil it. So you get a plume. That's what's indicated in this little diagram. That vapor plume coming off through the reaction force pushes down on the liquid metal, displaces it. You get a keyhole, as the welders like to call it, and that has many consequences. So to show you what you see when it's clean, there's no powder, versus what you see when you have powder present, you get these characteristic vapor holes, and sometimes they're stable, sometimes they are not. So this movie back here does actually show you the thing pinching off at the bottom and leaving behind these pores. And so it's been extremely useful for quantifying defect formation in situ, even operando, if you like. So the typical frame rate there is 50 kilohertz, but you can actually get to 10 megahertz and see lots and lots of detail. So that's fine in terms of visualization, but I think this audience is probably more interested in more detailed view of what's going on. So first of all, the cartoon gives you a slightly clearer picture of what it is that we're looking at with a beam. But now I'm going back to 1ID. I owe considerable debt to Andrew Chuang as the beam scientist who's helped us with this. And it was people like Kamel Fazar at 32 and Tao Sun before he left. So here we're back to using a monochromatic X-ray beam. We have a very nice detector, we typically call it the Pilatus, which has a large area detector. And that we run it typically at 250 hertz. And that allows us to capture complete Bragg rings as the melting is occurring, and more crucially, the resolidification of the material afterwards. And so this little view here gives you an idea of what the diffraction patterns look like as they're coming by. And for suitable conditions, then you do indeed see the material melt, diffraction goes away, then it comes back as it resolidifies. And the sort of elementary point is what phases were there before and what phases appear afterwards and at what times. So why do we care about things like that? Well, we're interested in, for example, nickel alloy 718. This is an alloy that has been around for several decades. The reason that we print with it is, along with 625, it's one of the few nickel alloys that is was known to be printable from the beginning, and that was based on its weldability. So you see a connection to sort of old line metallurgy, if you like. And the interesting point about this is when you print it and you apply some standard heat treatment, the microstructure that you get not only is organized with this very fine columnar solidification microstructure, but even a slight amount of heat treatment gives you this crisscross pattern. What you're seeing are particles of actually platelets of the delta phase. Delta phase is known, but you don't normally get this much of it, and it's not particularly good for properties. And so you ask, well, why is that happening? It's basically because of microsegregation. So that's a 2-micron micromarker. And so what it's telling you is that niobium in particular is heavily segregating to the interdendritic space. That's at first blush a surprise because of that very high cooling rate, 10 to the 6 per second. But it turns out that microsegregation can only be suppressed in a few circumstances, and definitely not in this material. So if you take those rapidly evolving diffraction patterns and you integrate around the azimuth, you can reduce it to this sort of streak diagram picture. And the time zero is at the bottom. And so time goes by, it melts, the diffraction lines disappear, however briefly. And then obviously the matrix, the FCC matrix reappears. But what you also notice is that some phases appear that were not there at the beginning, particularly the Larvis phases. And you also get certain carbide phases. So carbon is present at a small fraction. One of the reasons to do this at 1ID with its excellent energy resolution is you can see much smaller volume fractions of these second phases, which turns out to be very important in most engineering alloys. You're very often asking questions about fractions down to 1% or even less. So this was already very useful for, in a very accelerated way, illuminating what was really going on in these materials. Okay, so you can do the same sort of thing in stainless steel, and this is 316L, so L for low carbon. 316 stainless steel is a very standard material. And I mean, I'm putting it this way because it's very common in the scientific community, I have to say, that when you start talking about a material like this, people tend to say, well, isn't this a solved problem? Don't we know everything we need to know about this material? And the answer is, if you have the opportunity to measure something with a new tool, such as this high-speed diffraction, you run across things that you don't expect. And the don't expect consisted of this composition is supposed to be strictly FCC, but it turned out that for this particular experiment, when we looked carefully, we could find a frame in which it was very clear that the only phase present was actually the ferritic phase, the BCC phase. Not totally unexpected from the phase relationships, but really quite exciting to capture it, you know, in flagrante delicto, as you might say. And so we went on from that to say, okay, since we can actually see it and measure it, then we can do this as a function of the solidification conditions. And so these curves here are just showing you different temperature versus time histories for different combinations of power and speed, which give you clearly different cooling rates from slow, from the red one, to as fast as we can manage for the green. And what we able to establish pretty quickly, so that's cooling rate in the middle, and then ferrite fraction over here, is that there were measurable variations in that ferrite fraction as a function of time and as a function of cooling rate. So to what extent is this understandable? The answer is it should be understandable. And in terms of, as I said, phase relationships. And it turns out that what you have to look at is the ratio between chromium and nickel. It further turns out that stainless basically has to do with the chromium content, but most stainless steels are used as FCC materials, not the BCC. And most of these stainless steels, the composition is rather close to the break-even point. And what's even more interesting is that if you model what's going on at the dendrite tips, what you find out is that the actual local solidification temperature, which is reflective of the local driving force, varies as the solidification rate. So this is a case where it is quite sensitive to the solidification rate. Moreover, the dependence on rate is much stronger for the ferritic phase than for the FCC phase, the gamma phase. And so what that results is you expect ferrite at low cooling rates, but the FCC is going to win at high rates. And that crossover point is very sensitive to the exact composition. And so we were able to establish that some plate material had a different crossover point than a powder that is standard powder supplied for 3D printing. I can't say that we understand why these powders might be different from regular plate, and be shifted a bit towards the austenite stability, but it's certainly the result. And there are many microstructural consequences of that, but I don't have time to go into that. And so let me switch to another material that is also quite interesting, which is the standard alloy titanium 6 aluminum 4 vanadium. This is a classical high temperature BCC, low temperature hexagonal metal. So when you melt it and then refreeze it, you always see this high temperature beta phase. So the question is not which phase appears, as is the case for phase competition situations like stainless steel. It's more about how does that solid state phase transformation happen up around 1000 centigrade, because you have competing approaches. One is if you freeze rather slowly, then you get a diffusional transformation, a civilian transformation, as some would call it. Whereas if you go very fast, you get a martensitic transformation, or so-called military transformation, where the constituent atoms don't have time to diffuse long distances, and so you get the sudden shears in the crystal structure, and it, if you like, flips over from BCC to hexagonal. And it turns out that you can detect this in the diffraction information. If you go at a high enough rate, such as you see here, you see a continuity in the unit cell volume between the beta at height, that's the blue, and the hexagonal alpha, low temperature phase. Whereas if you go a bit slower, then you see jumps in unit cell size, jumps in the C over A ratio in the hexagonal phase, things like that. And crucially, the key difference is that we found was that the cooling rate required to have it be fully martensitic is quite a bit higher than reported in the literature. And that's very useful information, because if you're going to be able to take the process conditions and use those to predict microstructure and properties, this is information that you have to have. Okay, so I reckon I have about 3 minutes left. I'm going to talk about another stainless steel. I'm going to go back to stainless steel, but very briefly talk about a grade called 17.4 pH. pH stands for precipitation hardening. The 17.4 just indicates the composition approximate. And so again, we're using the high-speed diffraction to try to learn something about what's going on. And what I'm going to focus on in these diffraction patterns is one particular peak. So you see 4 different cooling rates, from low, quite low, to something more like what you would use in printing. And look at this individual peak here. It's the 200 reflection for the BCC. And you notice that there is a single peak at the very low cooling rate, but it's clearly splitting when you get up here. And you can have the FCC phase as well, and typically you see some of that, I guess, fairly consistently. But what was interesting in this was to look in more detail at this 200 peak and realize that the faster that we were going, the more obviously it was splitting into a main peak and a subsidiary peak. And then to further elaborate, this is the highest cooling rate. So you see the little movie of the diffraction patterns. And what you can see is the time dependence on that peak. And it's pretty clear that it's splitting very early on. Now, I don't have temperature associated with this, but here where the splitting is becoming clear, it's still pretty hot. I mean, it's going to be up around 1000 centigrade or so in that first, second, third, or fourth frame. And as you step through a slightly slower cooling rate, the splitting is still obvious from almost almost from the get-go. But as you slow down, then the split is still there, but it's just somewhat less obvious. And then if you go slowly enough, it really isn't there. And you would look at that and tend to say, well, it's just a single peak, and presumably we are only getting the VCC, whereas at the highest rate, we believe that we're seeing the martensite as well as the regular VCC, or maybe just the martensitic phase. And so this is something that remains unanalyzed. There's a lot to unpick from this, but I thought it was pretty interesting. All right, I'm out of time. I will show you one thing for bragging rights, as it were. Sorry, this.
You have plenty of time, Tony.
Okay, well, all right. So I take an extra few minutes and tell you at least briefly about what we've been doing with Bragg coherent diffraction imaging. Here, at least I have remembered to write down almost everybody that has been involved in this. Richard Sandberg, who was at Los Alamos, was very much a leader in this, although getting plenty of help from Sayu Fensin and Vijay Pokharel and others at Los Alamos. Tassos Pateras was postdoc involved in this. Stefan Hruzovic and Sid Medali have been very active in this. The beamlines, Ross Harder and Wonsuk Cha at 34. And I haven't written them down, but Jun Park and Peter Kennedy at 1ID have been closely involved. Matt Wilkin was in my group, and Yueheng Zhang. Anyway, not to make too much out of this. The basic idea is if your crystal that you're diffracting from is small enough, meaning fits within the coherence length of the X-rays that you have, which at the moment at moderate X-ray energies, 34 ID, for example, is about a micron. Then if you scan through an individual peak, what you see are fringes. And obviously, I'm showing you a sort of idealized example of this. And these fringes contain information about the phase field inside the crystal when you do a reconstruction, and moreover about the displacement field from which you can differentiate and learn something about strain. So the way that you retrieve the phase is very much a case of forward modeling until you get an answer that you believe in. And there are these classic methods of doing this. And the main things that we've been working on in recent times, obviously this originally started with getting an individual peak and reconstructing an individual grain. The problem with that, or the limitation of that, is it gives you information only along the diffraction vector. And if you want the full displacement field, as we surely do if we want to go hunting for dislocations, is you need at least 3 independent peaks so that you've got information in 3, you've got a basis set, if you like, for recovering that. And so we've been learning how to do coupled phase retrieval, where we're doing this on multiple peaks from a given grain. That was the main contribution of Matt Wilkin in my group for his thesis. There's more than one error measure. A crucial piece of this is the so-called support constraint or support function. In other words, you have to make decisions about what is the shape of the grain, but that's something you have to iterate on if you don't have independent information, but you can make it work. And so we have succeeded in doing this multi-peak Bragg coherent diffraction imaging reconstruction process. And from that, we have been reconstructing both made up data sets, simulated data sets, but also actual experimental data sets. So that's a simulated data set. So what I'm showing you here is contrasting what you see in the, this is actually error measure. if you do the sort of traditional independent reconstruction, that's the sort of error signal you see. With the coupled approach, you can significantly bring down the errors, and you don't have quite such a tendency for that error to be large near the edge of the crystal, which becomes very important if you want to actually look at defects close to interfaces. And then within the last 9 months or so, we're able to find pairs of twin-related crystals and do the reconstruction from a pair of twin-related crystals. And when you have an annealing twin, that's actually rather convenient, because that 60-degree misorientation about a 111 axis is very much the absolute minimum grain boundary energy that you can have, which means that that grain boundary tends to be very flat, reflecting that deep minimum in the energy surface. But that gives you a piece of prior information, if you like, about the shape of both of those crystals. You also know that if you are correct that those two crystals are in fact twin related, that misorientation is very precise. I mean, it really is 60 degrees plus or minus a tenth or less. Anyway, so what you see here is actually the first twin grain reconstruction, and actually coupling the two grains as well as coupling the multiple peaks from each one. And you do see a little bit of variation of displacement within the twin pair. And then very recently, meaning only last month, we went to 34ID with Richard Sandberg and company, held by Ross and Wonsuck. And we literally brought to bear a nano-indenter. So we found a twin pair of related grains, made sure that we could collect diffraction peaks, measured the twin pair, and then we poked at it with a nano-indenter. So these are isolated, in fact, de-wetted gold nanocrystals on a strontium titanate substrate. And we think that we succeeded. So in the following sense. So the top row are just 3 different views of the reconstruction phase map from the twin pair in the as generated state. And then what you see below is the same kind of map, but after we poked at it. And you can see that in the one crystal, there's distinctly something going on here. So that's interesting, but again, looking at the outside surface. This is, I confess, I'm not sure quite, I don't remember what the significance of these pictures are, so let me keep going. But what you see here is just flying through a vertical cut through these twin pairs. And on the left is what you see before poking at it. On the right is what you see after. And these are still the phase fields. But you can see even in the cross sections, both that there's continuity, reasonable continuity between the two crystals over multiple sections, and once again that something has happened in the deformed case. So this is the central cross section showing you 2 different slices, UX, UY, UZ. So just slightly different cross sections. That's before, that's after. So go back, before, after. And then finally, differentiating those fields to get strains. And what is particularly nice to see is on the top surface of the top grain, there's a rather obvious discontinuity here, and just magnify that a bit, suggesting pretty strongly that in all of the strain fields, all 6 components, there's what looks for all the world like, yes, we poked at it and we made a divot. It's like you came in with your golf club and actually scooped out something. So it's still early days in the overall approach, but the technique is definitely making progress, and it's been a very nice collaboration. Okay, so very quick summary. I don't think I need to read this out. Thank you very much for listening. I know it was kind of a smorgasbord of different topics, but hopefully of interest, at least in parts, to you, and I'm be very glad to take questions.
Tony, thank you very much for a very impressive talk. These are beautiful experiments and analyses. I'm really pleased you included the Bragg coherent diffraction imaging at the end, and the work with the indenter. We had tried some experiments that actually were quite successful many years ago, some 10 years ago, looking at gold using that technique in a diamond cell. So maybe we can talk about the possibility of doing that in a confined environment like a diamond cell under pressure. But anyway, let's open this up for others to ask questions. I see Brent has raised his hand. Just unmute yourself or put a request in chat. Go ahead, Brent.
Yeah, thank you very much, Tony. I also was very impressed with the technique required to do your study of the twins and the gold. But I have a question on the earlier part where you're seeing two phases in the stainless steel, the FCC and BCC. Do you have any evidence for chemical segregation in between the two, maybe over the diffusion time characteristic of the higher temperatures and the length scales you might get as you're forming the two phases?
The answer is yes. And I'm afraid I skipped over the microstructures, microstructural evidence. And it is notable, and let me make sure I read these properly. Yeah. So what you see on these two, well, certainly this one on the top left, was definitely in ferrite first and then austenite. On the other hand, if you get austenite first and then ferrite developing, you see this kind of microstructure in the part where it was first coming out as austenite, and then in between is the ferrite, and that's intercellular delta ferrite, and there's definitely microsegregation going on. So absolutely.
Is there a simple rule of thumb?
Well, we have not dived into trying to account for the microsegregation so much as just trying to understand the competition for which phase comes out first. And I don't know, I didn't include all of the evidence. Apologize for that, but we have seen this transition. We do have the direct evidence from the diffraction experiments that if you go slowly enough in either of these compositions, you will see ferrite showing up first. But as you go fast, when you go fast enough above some transition rate, and we're getting that about right, then the ferrite loses out and you get austenite coming out first, simply because the melting point suppression is less for the austenite as a function of speed.
Okay, thanks.
Yeah.
More questions, comments?
Yeah, Russ.
Yes, go ahead.
Tony, I wonder whether in your measurements of strains, did you ever observe very strong strain concentration at the tip of dislocation pileup? Right.
Very nice question. So the technique that I described, the high energy diffraction microscopy, is far too limited to look at dislocation tips. I mean, sorry, stress concentrations in front of dislocations. So in the HEDM part of it, the strain measurement pertains to the average strain in an entire grain. Now, there is a refinement of the near field technique that would allow us to refine the orientation map and develop maps of strain. That's something that Bob Suter has been working on. It exists in a sort of prototype form and still needs a lot of work, but it would return the kind of information that, at least in coarse grain material, would allow us to do what has been done in EBSD, high resolution EBSD. So people like Angus Wilkinson at Oxford. Now the BCDI, that's where we would indeed have the hope that we can actually image individual dislocations and be able to see the strain fields around them. And people, I mean, there are examples. People have shown, falling out of my head, the obvious references, but there are some examples. They're not actually on metals for the most part. It's, for example, that classic report on the nanoparticles of oxides.
Okay.
Tony, can I maybe add something to that? This is Saryu.
Oh, hi, Saryu.
Hi. So I think one of the things that, just as a reminder, that we're trying to do is also combine MD with some of the strain maps that we're getting, right? So we could simulate a pileup as an example, and then try to see what does that strain map look like. So when Richard and I first started looking at BCDI, we did take a copper bicrystal or copper film, pulled it, and we got a strain field that looked like a screw dislocation. We weren't sure, so we did some MD, and then we're able to say, you know, model different defects, and said that the screw dislocation gives us the best match. So hopefully we'll apply those type of analysis techniques to these results as well.
Oh yes, I mean that is very much my hope that we would be able to go back to I'm nowhere near. Where did he go? Wait, somewhere, yeah, here. Go back to these maps and look in more detail and say, yes, that, you know, there have to be dislocations. If that's an indent, there have to be dislocations sitting underneath the indent. And be able to, probably through some kind of forward modeling exercise, reconstruct that network of dislocations and model from there.
Okay, thank you both. And you know, reason why I'm asking, because in high pressure experiments on the large plastic deformation, we are getting reduction in phase transition pressure by factor of 10 to 100.
Oh.
Yes. And the only way I can imagine is that plastic strain injects dislocations pileups, and at the tip of dislocation pileup, you have very strong multiplication of stresses, and that is what causes phase transition at lower applied pressure. And we have proof, theoretical, analytical, with two different phase field approaches, with molecular dynamics and with concurrent MD and finite element continuum approaches. But it's great, would be great to have any experimental proof, you know, and this effect is so huge that it should be visible, you know. And also what we found, that this dislocation pile up in simulation, it's localized at grain boundary. Right. So it should be a large step, and it's independent of grain size, which is important, but it's just focused at grain boundary.
Yeah. Which makes my head race along in terms of, you know, what kind of beam should we send through it and how to interrogate it. And Saryu is probably ahead of me in terms of having thought about the problem. But yeah, there are a number of different ways that one could try to sort of creep up on the problem, as it were.
It would be great.
Yeah, yeah.
I agree, and it comes back to my first point about doing this in situ in a diamond anvil cell.
Oh, yes, of course. Right.
You would see exactly what Valeria is talking about in situ. You could follow it, not just with an indenter, but you have an entire anvil. deforming the sample.
Well, I mean, I think the obvious requirement is to get a highly monochromated beam into and back out of that crystal and be able to interrogate it in various ways.
Right, very good. More questions, comments? If not, Tony, thank you very much for this wonderful talk.
All right, my pleasure. Thanks for the opportunity
Thank you, Tony.
to speak.
Okay.
Very
Thank
good.
you all for joining us.
Yep.
See you next time.
See you. Yep. Cheers.